All right, y'all. We're going to do a video on section 2.5. What we're going to be looking at right here is transformations of functions. And the first thing that I'm going to go over really quickly is I'm going to go over just a basic kind of overview of some general function types that you should absolutely be familiar with, because this is kind of going to be what we're going to use to transform all of the functions that we see in this section. The first type of function is a constant function. You can think about this as like a straight horizontal line where it's just remaining constant. The second function is going to be an identity function, which is just going to be a diagonal line slicing the plane kind of in half through the origin right there, right? And this is kind of in the line with our linear functions that we looked at in the last section, the functions that were like of a line, right? We're going to look at the absolute value function. This is much like the identity function, except for the negative side of the graph over here, it's going to be actually all positive. A good way to think about what this function does is that it's going to take any negative input and it's going to make it positive. And if it's already positive, then it's just going to be where it is, right? So if you have -2, it's going to +2. If you have 2, it's going to +2. So it just makes the negatives positives and it keeps the positive positive. Here we have a quadratic function. This is just going to be y is equal to x squared. You can see it's given by that function right here. And we'll talk more about all of the remaining functions down here in later sections, but for now we just need to know what the general shape looks like. And for these ones that are a little bit more complicated right here, I'm going to recommend kind of knowing some key points of interest for this kind of graph right here. For example, if I have f of x is equal to x squared, then that means that 0, 0 is a point, 1, 1 is a point, -1, 1 is a point, and then also it goes a little bit off the graph here, but 2, 4, and then -2, 4, right? So those are kind of some helpful points you can use to help transform this one. Square root function is just f of x is equal to the square root of x. This one has some nice points as well at 0, 0, and 1, 1, and also at 4, 2, because the square root of 4 is 2. One nice thing about this one also that you have to keep in mind is that it's only going to be defined on the positive x values, right? You cannot have a negative number inside of a square root, because if we think about what is the square root of -4, there's no real number that we can multiply by itself to get a negative number. If you do +2 times +2, that's just going to be +4, not -4. And if you do -2 times -2, that's also +4. So only positive numbers are going to work inside square roots if we're only worried about real numbers. The cubic function is going to be like the squared function over here, except you're just going to cube it instead of square it, right? Some more nice points are 0, because 0 cubed is just 0. 0, 0 is a point. 1 is also a nice input, because 1 cubed is +1. And then -1 is also a nice point, because -1 cubed is also -1. So those are 3 points that you can kind of have memorized for the cubic function. And then the last one that we'll look at is the cube root function. This one, it does make sense to have negative and positive inputs, because then you're asking what number cubed is the number that's given right here. For example, if I cube 1, then I get 1. If I cube 0, then I get 0. And if I cube -1, then I get -1, right? Also, you can think about it in the terms of the higher ones as well. Like if you cube 2, then you get 8. So that means that 8 over here should lead to 2 as a cube root. If you cube -2, then you get -8. So -8 should lead to -2 from an input to an output. These are all functions that you're going to need to be familiar with, the shape-wise at least. That way we can use them to kind of quickly graph these transformations, as we'll see below. Let's look at just how some of these general behaviors are going to occur on some of these graphs so that we can get an idea for how these transformations are going to occur. Let's look at example 1. It asks us to graph a few different things and then observe the changes in them. So example 1. I'm going to be graphing all of these on the same plane just to get an idea of how they relate to each other. So we have f of x is equal to the absolute value of x, f of x is equal to the absolute value of x plus 2, and then f of x is equal to the absolute value of x minus 3. Let's put these all on the same plane and then see how they are going to compare graphically to one another. I'm going to use different colors for each of these. Maybe I'll use blue for the absolute value of x, and then other colors whenever we get there for the other ones. Let's add some tick marks. Maybe I'll go out just 3 in each direction for now. We'll start with the absolute value of x. This first function is just that absolute value function. So we know that 0, 0 is a nice point. 1, 0 is a, or sorry, 1, 1 is a nice point, and then negative 1, 1 is a nice point. And we know that it kind of makes that V shape that are going through these points right here. So our general function for just the absolute value should look something like this, where we have kind of a V going between those given points right there. Now, let's think about what's going to happen if I start looking at the changes to maybe the next function, which we'll do in red. Well, if I input 0 into this function, then the absolute value of 0 is 0, and then I'm adding 2. So 0 is actually going to go to the value 2 instead. If I input 1, it's going to go to 3 instead. And if I input negative 1, the absolute value of negative 1 is positive 1, so it's also going to go to 3. So if we look at the behavior of what's going on with this function right here compared to the other one, it looks to us like this function is getting shifted up by about 2 units from the blue to the red function. That is, in fact, what is happening. Let's do the other one in green. Well, if we added 2 to the function and it went down, or sorry, it went up rather, by 2 units, then whenever we subtract 3, it should move down by 3 units. And we do end up seeing that's what happens. We move that 0, 0 point down to 0, negative 3. We move this point down to 1, negative 2, and then negative 1, negative 2. And again, we'll get this absolute value like structure there, where this is the absolute value of x minus 3. So what it looks like to us, and I kind of messed up my line a little bit right there, but really the only change between these functions should be where it's shifting to. The blue one is the original one. If you're adding something to the entire function, it's shifting up, and if you're subtracting, it's going down. Let's look at example 2 and see a different example. Let's look at what happens whenever we instead throw values inside the function. So we're going to look at f of x is equal to x cubed, f of x is equal to x minus 1 cubed, and then f of x is equal to x plus 1 cubed. And again, we'll do the same thing. We'll have a different color for each one of these. Okay. So first thing is we'll just look at x cubed, and again, maybe I'll move out some of these in each direction right here. And the first one that we'll graph is the x cubed function. Again, we saw that this one was one of the ones that we just needed to have memorized. We know there's a point at 0, 0, a point at 1, 1, and a point at negative 1, negative 1. And we know that it does this kind of squiggle behavior through the origin, and then it tails off in either direction. Ooh, that was kind of bad, but like this. So something like that, right? Kind of messed up on that bottom tail right there. But that's a general idea for the cubic function. For the other variations of this, let's see what happens whenever we first subtract one from the inside. Notice that this is different than what we saw up above because we're not subtracting 1 from the entire x cubed, we're subtracting 1 from the x input first and then cubing it afterwards. What we actually see here is that if we input 0, we're actually cubing negative 1. So 0 as a value goes to negative 1 cubed. And then if I input 1 here, that actually goes to 0 because 1 minus 1 is 0 and 0 cubed is that. And then if I input maybe 2, 2 is actually going to go to 1 because 2 minus 1 is 1 and 1 cubed is that. So what we see here is actually we take this entire function and we're really just shifting it over by 1 unit right there. Something similar happens whenever we look at x plus 1 squared, but we're actually going to be moving in the opposite direction. We can see that we're going to be shifting it over. If I plug in 0, I actually get positive 1. If I plug in negative 1, I get 0. And if I plug in negative 2, rather, I get negative 1. So you can see I shift everything over to the left right here. And I have these 3 instead. So whenever you add a number inside the parentheses directly to the input, you're actually shifting over to the left. And whenever you subtract a number from the inside to the input, you are shifting over to the right instead. Okay, so that's another interesting thing to notice right here. Let's look at example 3. Example 3 is looking at the square root function. We're looking at f of x is equal to the square root of x. We're looking at f of x is equal to the square root of negative x. And we're also looking at f of x is equal to negative square root of x. Whoops. There we go. Kind of did a broken squiggle right there. Looks like there's actually something in my table. Oh well. Okay. So, again, what we're going to do is we're going to start out with just graphing the square root function first. I'm going to do my tick marks out in each direction like I did last time, just to give me something to start working with. But for the original square root function, we have a point at 0, 0, because 0, the square root of 0 is 0. The square root of 1 is just 1, and then if we wanted to, we could also do the square root of 4, which is 2. Or, the square root of 4 is 2. This gives us just the original graph of the square root function, which looks something like this. Again, remember, this is the weird one that's not defined on negative values just for the basic square root, right? So we're only going to have it tailing off to the right. However, if we look at what happens whenever we take the negation of that inside bit, we're actually going to be using all of the negative numbers. Well, if I plug in 0, 0 is still going to be a point right here because negative 0 is still just 0, and the square root of 0 is 0. Here, if I plug in negative 1, though, negative 1 is positive 1. So that means that the square root of positive 1 is going to be 1 right here. Notice that if I plug in any positive values, it's actually just going to be negated. I can't do 1 because then that would be negative 1 inside of here. The only other point that would work would be negative 4, because negative 4 would be positive 4, and the square root of that would be 2. So what we see here is whenever we negate that inside of the argument right here, it actually kind of flips all of these points over the y-axis. We're flipping them or reflecting them over the y-axis. So that's an interesting observation. Let's look at the other one where we're negating the output instead than negating the entirety of the function. Here, we're not changing the sign on our input, we're just changing the sign on our output. So whenever we plug in 0, the square root of 0 is 0, and negative 0 is still 0. So that's still going to be a point on the origin right here. But whenever we do 1, the square root of 1 is 1, but then I'm negating that afterwards. So 1's actually going to negative 1. Similarly, 4 is going to go to negative 2. So what I'm actually going to have is this situation right here, where I'm reflecting not over the y-axis this time, but the x-axis, if I'm thinking about it in comparison to the original blue function. So the basic function looks like this. Whenever you negate the input, that x value, it looks like it's reflecting all of those inputs over the y-axis. And then whenever you negate the output, it's reflecting all of those outputs across the x-axis. So we have reflections going on whenever we're adding these negative signs either to the entirety of the function or the input itself, right? So that's also another important property that's going to help serve us here. Let's look at example 4. This is going to be the last important type of transformation that we're going to look at. For example 4, we're looking at f of x is equal to x squared. We're looking at f of x is equal to 2x squared. And then we're looking at f of x is equal to 1/2 x squared. Okay? Again, I'm going to graph all of these on the same plane, so I'm going to go ahead and start sketching that out for us. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9 maybe. And then 1, 2, 3, 4. That should be enough for what we need right here. Maybe I'll add some down here, but we're not going to need them. Again, we're going to start just by graphing that x squared function first. This should be one that you should recognize. Again, all of the ones at the beginning, those 7 that we talked about, should be ones that you're able to recognize here. And for the x squared function, we have a point at 0, 0, because 0 squared is 0. 1 squared is 1. Negative 1 squared is 1. And then I'm going to go ahead and add a couple more. 2 squared is 4. And then negative 2 squared is also 4. So I have a good number of points right here to kind of get me a good representation of what this graph should look like. This is just the basic x squared graph right there, okay? Let's look at what happens whenever I take this function and then multiply it by 2. So if I'm looking at the next function, 2x squared, it looks like all I'm going to be doing is still squaring that value and then multiplying it by 2 afterwards. Notice that 0 is not going anywhere because 0 squared is 0 times 2 is still 0. But whenever I plug in 1 now, 1 is actually going to move somewhere, right? Because 1 squared is 1, but then I have to multiply that by 2, so it's going to go up. The same thing is going to happen with this one right here. If I think about what happens with 2, well, 2 squared is 4, and then I have to multiply that by 2, and that's going to get me all the way up to 8. So I'm going to move these 2 points up even further like that. So if you see what's happening here is it looks like I'm kind of compressing that function towards the y-axis, or I'm vertically stretching it along the y-axis, along the x-axis. Either way that you would like to think about that. Here it kind of makes sense to me that it's being squished towards the y-axis, or kind of being, the y values are going to be stretched out, so further away from the x-axis. Either way that you would like to think about that though. Now that's what happens whenever we multiply by, a number that's larger than 1. Let's look at what happens whenever we multiply by a number that's less than 1. 1/2, for instance. Well, we're going to do the same idea that we did before. 0 squared is 0, but this time times 1/2 would just still be at 0, so I still have that point on the graph. But now I have to take half of these points that I have right here in the y direction. So for example, whenever I plug in 1 squared goes to 1, and then 1/2 of that would be somewhere around this area right here, because 1 is going to 1/2. -1 would also be going to 1/2. And then these points right here, 2 squared goes to 4, but 1/2 of 4 is at 2. So it's actually getting knocked back down here and here. So it looks like I'm actually kind of squishing my function down a little bit and flattening it instead of kind of compressing it towards that direction, right? And you can see this is going to be basically the difference between what's going on and being multiplied here. This blue function being our original function is just the original function. Whenever you multiply the whole function by a number that's greater than 1, 2 for instance, it's going to stretch it vertically in this direction. It's going to get stretched out. And whenever you multiply it by a number that's less than 1/2, it's going to compress it vertically, right? So those are kind of the two different ways that we can go about looking at that, right? We're going to come up with a more robust terminology for this in just a moment, but for now we'll kind of leave it at that, okay? Let's look at the next example real quick before we actually formally define all of these. Example 5. Example 5 asks us to graph the following just by using transformations. The first one that we'll look at is h of x is equal to -x plus 1. And now, before we actually do this, I am going to go ahead and move that paper from the beginning back into view. We just did examples 1 through 4. I want to take a moment to kind of look at all of the different transformations that we just talked about, and then we'll use them to talk about this example 5 real quick. So here's a summary of all the different transformations that we can really do for these graphs. We saw that we had a shift of a vertical variety whenever we were adding a value to the entirety of the function. That was like the very first thing that we did whenever we shifted that absolute value up and down. We shifted horizontally in the left and right direction, like this example with the cubic function whenever we were adding or subtracting to the input directly, not the entire function. We saw that there was reflections whenever we were taking the negatives of functions, either the negative of the entire function, which led to a reflection about the x-axis, or a negative of the inside of the function, the inputs, which led to a reflection about the y-axis. And then finally, we just talked about these vertical stretches or vertical shrinks. We're not going to worry about these horizontal ones for this class actually, so we'll only worry about the stretching vertically and shrinking vertically. But you stretch vertically if c is greater than 1, and you shrink vertically or compress if it is less than 1, right? So just to kind of double back on that terminology right here, this one, the blue one, would be the original one. Red would be an example of stretching since it is greater than 1, and then green would be an example of shrinking since it is less than 1, okay? Now that we have that out of the way, let's go ahead and use all of this information to go ahead and graph these guys. There is one other small note at the bottom here that will come into play, and specifically it is that we have to make sure that we are following the order of these transformations in this order every time. Do your horizontal shifts first, your stretching, your shrinking, your reflections, and then finally your vertical shifts, okay? This is going to ensure that we basically follow order of operations, and I'll explain that as we kind of look at this first example, okay? So if we're looking at example 5, we might notice that there are multiple different kind of transformations taking place here. Not only do we have a negative, but we also have this plus 1 right here. Well, because we have those multiple transformations taking place, we're going to want to make sure that we account for both of them and do it in the correct order. Well, first we need to do any horizontal transformations that we have. And here we see that we are adding 1 to the inside of the function. So this is going to end up being a horizontal shift. And remember, since we're adding, it's actually going to be to the left 1. So that's kind of one thing that's happening right here. And that is denoted by this blue thing that I'm underlining right here. So that's what tells me that I have this horizontal shift going on. Now the negative sign is going to result in a reflection, right? Now, remember, we have to decide whether that reflection is going to be over the y or the x-axis. And here, since the negative is inside the function, it's going to be a reflection about the y-axis. So reflection over y-axis. I'll go ahead and underline that negative right there. And again, the reason why I'm picking out these two things, this +1 and this negative, is because if I'm thinking about what the quote-unquote original function would look like, I'm just comparing this in my head back to the square root of x. So for example, this differs from the square root of x with this negative sign right here and this +1. What this is going to allow me to do is it's going to allow me to start with the function that I know the graph of, this square root of x, and then it's going to allow me to get to this function down here via transformations. So let's go ahead and look at that. Excuse me. Let's first graph the square root of x function. I should add some tick marks to this graph first. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. There we go. So by adding tick marks to this graph, we can go ahead and graph this just the square root of x. This one we should know that it looks something like this. Again, look back in the video if you need a reminder on how to graph the square root bit. But this is just the square root of x. And now, if I wanted to graph what the h of x function that I'm interested in should look like, I know that I need to take this function, shift it over to the left 1, and then reflect it across the y-axis, okay? So what I'm going to do this is I'm just going to follow these 3 important points that I've made through those transformations. You can see that I have a point at 0, 0, at 1, 1, and then at 4, 2 right here. So first, I'm going to take this point, shift it 1 over, and then reflect it across the y-axis. I'm going to go ahead and label my y and x-axis just for clarity. So shifting it over 1, and then across the y-axis, reflecting it, would land me right here. So this first point ends up 1 to the right. Again, what's happening is 1 to the left and then reflecting, but it ends up 1 to the right. If I think about what's happening with this point over here, the next point, I shift it over 1 to the left. I reflect it about the y-axis. It's right on the y-axis, which means that it's just going to stay on it, and then that would be my second point. For my final point, I need to shift it over 1 to the left. You can see I'm at this 3 value mark, so that means whenever I reflect it over to the across the y, the x value needs to go from +3 to -3. So I should end up somewhere right here. And then I can draw a smooth continuous curve through these points to get my square root function. And I kind of curved down a little bit too much right there. But it would look like something like this. And this would be a good graph for my h of x function. This would be the graph of -x plus 1. And this is going to be the general strategy that we take in this section. We're going to start by sketching what the original function, the function that we know what it looks like, would look like. And then we're going to identify what transformations make it different from the original function and use that to graph the next function. Okay? Let's look at a couple more examples. That was A. Let's look at B. This one gives us g of x is equal to 2 times the absolute value of x plus 3. All right? Again, what I would recommend doing is starting out with any transformations that you need to do. First, look for horizontal. It looks like we do have a horizontal transformation. So we'll say h shift, horizontal shift, by -3. So we need to go left 3. I said -3. Here, because I'm adding 3 in the inside of the parentheses right here, it's, excuse me, like I'm subtracting a -3. So that's why I need to move to the left. Again, you can refer back to this part of the notes where you kind of have a summary of everything that talks about whether it's being shifted horizontally left or right. This is something that you're going to have to know, though, and have down pat. So while you're referring to it in the notes for now, you're going to need to have it memorized at some point. The only thing else that makes this different from just the original absolute value function is going to be that 2 out in front. And remember, this is what we called a vertical stretch. So we can say vertical stretch by a factor of 2. And now we can just go ahead and do what we did last time. Do a quick sketch of what everything should look like here, starting with that function where we should hopefully know what it looks like. The absolute value function is going to have a point at 0, 0, 1, 1, and negative 1, 1. And then you're going to have that v behavior that's cutting through the, or not cutting through, but bouncing off the origin rather. So there's our absolute value function. Okay? And now, for the transformations, what we need to do is we need to take those reference points that we have on there, and we need to send them through these transformations. So let's start with the leftmost point. We're going to take this guy, shift him to the left 3, and then vertical stretch him by 2. So moving this point to the left 3, 1, 2, 3, and then a vertical stretch by 2 means that we're actually going to multiply the y-coordinate by 2. Well, the y-coordinate on this point right here is 1, so that means that I'd actually need to move him up to 2 because 1 times 2 is 2. So I'd move him right here. So this point is getting moved over 3 horizontally, and then the y value is getting stretched by a factor of 2. Here, I can do the same thing with the origin point, move it over 1, 2, 3, and then since the y value here is 0, whenever I multiply 0 by 2, it's still just going to be 0. And then finally, I can do the same thing with this last point, move it over 1, 2, 3, and then up right here. And you can see that whenever I connect the lines right here and do that same behavior, I still get that absolute value behavior, but this time it is vertically stretched by 2 and then shifted over 3. And that would be the actual function that I'm interested in for this one. This would be 2 times x plus 3, right? Wonderful. Let's look at one more of these before we shift our focus slightly, okay? I'm gonna move this out of the way. Example 6. C. The last one that we'll look at is f of x is equal to negative x minus 3 squared plus 4, okay? What I'm noticing here is that this is most close to the just x squared function, but I have really 3 different things that are different than it. Firstly, if I'm looking for my horizontal transformations first, remember I have to do it in that order that was at the bottom of that chart. My horizontal is going to be is going to be shown by this negative 3 value right here. This is going to represent a horizontal shift in the right direction because I am subtracting 3 from the inside of the argument. Next, it says I want to look for any stretching or shrinking. I don't have a number being multiplied by the function here, so I'm not going to have any stretching or shrinking. I am, however, going to have a reflection because I have that negative sign right there. Remember, a negative applied to the entire function, not the inside but the outside, is going to represent a reflection over the x-axis. So I need to reflect over x-axis. That takes care of the negative transformation. And then 3, the final transformation that I need to do, is that vertical shift. So I have a vertical shift up 4 units, right? And again, just to highlight where each of these are coming from, this is going to be the shift by 3. This plus 4 is going to be the up 4. And then this negative sign right here is going to be the reflection over the y-axis, okay? Now that I have each of these, I can go ahead and graph what my x squared function should look like, and then apply whatever transformations that I need to apply in order to get the function that I'm actually interested in. Y and x. So for the x squared function, we have a point at 0, 0, 1, 1, negative 1, 1. And we can connect those points as such. And then what we need to do is we need to take those points that we have as those reference points right there. Again, I would at least recommend having 3. Oh, I went way over to the left there. Apologies. I would recommend at least having 3 of these guys. and then follow them through these transformations. This time we have 3, so we want to make sure that we're following them appropriately. I'm just going to take the very leftmost point first, and then we'll follow this through the transformations. First off, shift it to the right 3, so 1, 2, 3. Reflect it over the x-axis, so I'm going to be making the y value different by shifting it over the x-axis. Now I'm here, and then I need to vertically shift it up 4. 1, 2, 3, 4. So it looks like I'm going to follow that transformation one more time, shifting it over 1, 2, 3, across the x-axis, and then up 1, 2, 3, 4 should end me right here, I believe. I'm going to do that one more time to make sure we end it in the right spot. 1, 2, 3, across the x-axis, 1, 2, 3, 4. Okay, so that takes care of my first point. Let's do the other one. Shift it left 3, 1, 2, sorry, right 3, 1, 2, 3. Reflect over the x-axis. It's on the x-axis, so it just remains there. And then shift up 4, 1, 2, 3, 4. Then the last one, shift over 3, 1, 2, 3, down over the x-axis, and then 1, 2, 3, 4. Oh, whoops, I didn't go up quite enough. There we go. So again, following this point one more time, I accidentally made that additional mark there. Apologies, that one's not correct. But here, I move over 1, 2, 3. I shift it across the x-axis right here. So now I'm right here, and then I need to shift it up 1, 2, 3, 4. So I'll have this kind of behavior on my graph instead. So this one had quite a few transformations to follow right here. If you need to draw a couple graphs to represent multiple steps here, you're more than welcome to. Here we kind of combined all of these steps into kind of a one process right here. But this blue function would represent the final function that we're after, and then the green function would just be the very basic x squared function that we use to achieve this, along with those transformations that we listed over there. Okay, wonderful. Let's go ahead then and look at the last kind of example that we'll need to look at in this section. I'll do example 7. Now, example 7 actually gives us a graph, and we'll kind of use that to help with this problem right here. Let's go ahead and sketch the graph that it's giving us first, just so that we have reference to that. I'll sketch it here. And then we'll sketch the transformed version over here. All right. So the graph that it gives us, it looks like needs to go 5 tick marks out in each direction. So I'll start with that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, here's our x and y. And the points that it gives us for this function is going to be at -4, -2. -4, -2, so right here. Looks like it goes up to 0, 2, so right here. Goes over to 2, 2. Is that correct? It does go over to 2, 2. And then 4, 0, so right there. And the general behavior is just, this is a straight connections between all of these points that we've drawn right here. So that's the function that we're dealing with right here. We kind of have these 4 reference points that it's given us, so I think that we're probably going to want to transfer all of these through whatever transformation is going on. And the function that it actually gives us to transform, this is what it is calling the f function, f of x. And it is saying the g function below is g of x is equal to negative f of x minus 1 plus 1. Okay? Well, this is actually representing to do another 3 transformations, kind of like what we did in the previous problem up there. And we'll go ahead and list them out maybe below this, and then we'll come back up and actually do them. So the 3 transformations are first going to be a horizontal shift, because we see there's a horizontal shift on the inside. We're subtracting 1, which means we're actually going right 1 unit. Then we're reflecting again over x-axis, because we're taking the negative sign of the entire function. So reflect over x-axis. And then 3, we're doing a vertical shift up 1. So these are the 3 transformations that we need to send all 4 of those points through in the previous problem right there, okay? I'm gonna go ahead and move this back down, and we'll look at doing all of those transformations, okay? I probably should go ahead. Actually, I'm going to go ahead and do the transformations on this one graph, just because it's probably going to be a little bit easier to follow them if I do it here, okay? So I'm going to do it in maybe red for g of x. That's what we'll do the g of x function in, since I've already used green for the f of x function. And we're going to take the points, and then we're going to follow the transformations. So the first one is a reflection over, a horizontal shift over 1. So I'll move that point horizontally over 1 right here. Reflect over the x-axis, so then I'd be up here, and then vertically shift it once more up. So then now that I'm right here, I need to go one more time up to get here. Follow that one more time. Horizontal shift, reflection over x-axis, and then, wow, I completely messed up my x and y labelings over here. I'm sure y'all would have caught that for me in class. X and y, there we go. The point is in the correct spot, I just mislabeled my axes, apologies. So here, I go, again, over 1, reflect over the x-axis, and then up 1. Do the same thing here. Over 1, reflect over the x-axis, and then up 1. Gets me right here. Over 1, reflect over the x-axis, and then up 1. Over 1, reflect over the x-axis, I'm already here, and then up 1. And it looks like if I do those same connections between these points, that I will get something that looks like this. And this will be my g of x function. And that's what the function is actually, or that's what the question is actually looking for, is the sketch of this red graph right here. So by following those function transformations, by shifting each point over 1, reflecting it over the x-axis, and then vertically shifting everything up 1, we can achieve that red function right here. Again, I thought maybe we would sketch it on 2 different graphs, but I don't think that was actually necessary for this one, okay? That's all that we're going to talk about for this 2.5 section. I'll go ahead and end here.